So the iCub has left Italy for a number of European laboratories, including my robot cognition laboratory in Lyon. Here at the INSERM Stem Cell and Brain Research Institute, we perform fundamental brain research to understand how the brain allows human language. We then implement this language capability in the robots to allow them to negotiate cooperative shared plans.
You have moved the trumpet.
This means that we can make the link between language and action to begin to cooperate with the robot.
So here the idea for the iCub is to find the object I have moved and grasp it.
How can I help you?
Shared plan.
Shared plan menu.
You and I play toy box.
Tell me how you and I can play toy box. What is next?
You put box right.
I will put the box on the right.
Here, Stefan explains the shared plan to the iCub.
You and I play toy box.
It's a game where one of them will uncover one of the toys and the other will take it.
I will put the box on the right. You will put the toy on the left. I will put the box on the middle.
As soon as the robot has learned the plan, it can use the same plan even with different objects. It's actually learning to cooperate. The robot describes the shared plan it has just learned and then begins to execute it with Stefan. Each performs his action in the sequence that Stefan has just taught the robot, and together they reach their shared goal of uncovering the toy. This learning in real time is one of the unique capabilities in the project. So it's interesting how his gaze was actually directed at you, almost as if he was trying to tell you what to do.
What we found is that the eye contact between the robot and the subject is very important, because when the robot is looking at you, fixing your gaze, then it's like if he's expecting something from you. And as a human, you want to try to understand what he asks you.
Within the CRIS project, we've extracted principles of cooperation from the child studies in order to develop a cognitive architecture that allows the robots to cooperate with people. So robots, in order to interact with humans, they need to be able to see and they need to be able to move. So on the seeing side, the eyes, the ears, the muscle proprioceptions feed in to the scene perception module of the robot. So this provides the ability of the robot to represent the visual scene, what's going on around it. So in addition to perception, the robot also has to act. So we've created the motor command level where information about where objects are in space is transformed into actions directed towards those objects. So this is like the human capability to produce action with our muscles. Now the robot can see and it can act. And as time goes by, it's accumulating knowledge about what it's done. So we created the knowledge base that allows the robot to store this information and retrieve it. The knowledge base is fed both by the perception system and it interacts with the motor system. So at the final level, we introduce the supervision and planning capability where the robot can learn new shared plans in order to cooperate with people, learn decisional planning, execute sequences under the control of supervision, and so this provides the highest level of cognitive function that allows the robot to cooperate, like the children that we saw in the developmental studies.